For this video, we describe the concept of Le Chatelier's principle. For this principle, we look at what happens when we add a stress to a system and how that system will shift its equilibrium in response to that stress. So for Le Chatelier's principle, there are two key steps. One is that there is a stress applied. In lab, that is something that we can do to a system. And then the second step is to identify the direction of shift for that reaction to come back to equilibrium. So in other words, when we apply these stresses, they cause the system to shift away from equilibrium. Of course, that makes the system unhappy, and so it wants to come back to equilibrium by shifting left or right. And there are some cases where there's no shift. We'll discuss those as we go through. For the stresses that we'll be discussing, we can talk about changes in concentration. So both of these first ones can be generalized as concentration changes. We can increase the amount of a reactant or a product. And when we say concentration, we can mean pressure too, adding more of a substance. So we can increase the amount of reactant or product, or we can remove or decrease a reactant or product. That is harder to do, but not impossible. We will discuss a change in temperature, and we will discuss a change in volume or pressure. And we'll talk about these together. Hopefully you remember from first semester that there is an inverse relationship with those, that as we increase the pressure on a system, the volume of the container will decrease. And there are a few other changes we'll discuss at the very end that are very minor. Now, the nice part of Le Chatelier's principle is that it's not a mathematical topic. I'm going to show numbers as an example here to illustrate how our previous discussion of Q versus K can help us determine the direction of shift. But for the most part, for this section, we're just identifying directions. But to begin with, we'll look at the formation of ammonia from its elements. At 540 Kelvin, we measure these pressures at equilibrium. Plugging those into our equilibrium expression, here are our values, and we get this equilibrium constant, again, at that temperature. Now, for this system, the stress that we're going to apply is that we're increasing our hydrogen concentration. Realize that we've increased it by 1 atmosphere. Right? We started at 2.319. We're going to add more hydrogen into the system. From a conceptual standpoint, it should make sense that if I'm introducing more hydrogen into the system, there's more hydrogen that's available to react with the nitrogen that's already there to form more products. So remember, at equilibrium, we have a little bit of everything in our reaction container. So when I say that this is at equilibrium, I actually have all three of my nitrogen, hydrogen, and ammonia present. So all I'm doing is putting more hydrogen into the system. I'm increasing this. That means there's more available to react with the nitrogen. So again, I can make more ammonia. Now again, from a calculation standpoint, what this means is since I've disturbed equilibrium, I now have to calculate a Q value. Again, we have our same setup as K. We plug in our values and recognize that we get this Q value. So realize I've increased my number in the denominator. So it makes sense that my Q will now be less than K. Anytime Q is less than K, it means that Q needs to increase, and that happens when our system shifts to the right. So both qualitatively, thinking about the reaction with hydrogen, and quantitatively, calculating Q, we determine this reaction should shift to the right. Again, from a graphical standpoint, from this first part, these were our initial values at equilibrium. Here is the moment where we increased the pressure of hydrogen, and then it takes some time for our system to come back to equilibrium. So at this point, we reach a new equilibrium. So the interesting thing to note here is that we do have new equilibrium quantities for all of our substances. They are not exactly where they were before. right? Notice our colored lines are in different spots. But what stays the same once these come to equilibrium, if you plug in these approximate values, when we plug into our Kp expression, notice that we have virtually the same value of K that we had before. So even though each individual substance has a different equilibrium amount, the ratio of products to reactants, our K value, remains the same. For this slide, I'm going to walk through, as soon as I get rid of that table, there we go. I'm going to walk through changes that we see when we change concentrations, or the shifts that we would see when we change concentrations in a reaction. So again, we really have four options. We can increase a reactant, we can increase a product, or we can decrease those. Well, we just saw from our numerical example with the ammonia equation that when we increase the amount of a reactant, realize that the system wants to undo the stress that we've applied. So we added hydrogen, we increased the reactant. The system wants to undo that, and it'll do that by forcing the hydrogen to be used up. And it does that by shifting forward. Same idea, if we were to increase the amount of a product, if I introduced more ammonia into our previous system, the system wants to get rid of that excess ammonia. And again, remember our equation that we were working with is here. Formation of ammonia from diatomic nitrogen and hydrogen. So again, if I were to increase the amount of ammonia in here, the system wants to use that up, and it's going to do that by forcing this reaction in the reverse direction. So it's going to help break down that extra ammonia into its elemental forms. Now, again, decreasing amounts of reactants or products, same concept. We're obviously just reversing these. These are a little bit trickier to do because in order to remove something, so realize that for this reaction, everything is a gas. So I can't just reach into a container with a syringe and try to extract one of these. I would get a sample of everything, right? It's in equilibrium. They're all moving around freely. So the easiest way to remove something is to actually introduce something that causes a side reaction that would react with one of the substances in here and remove it. So I have a really horrible example here, and this would never happen, and it couldn't happen, but pretend, just bear with me. So let's say we have this ammonia equation. I have all three substances in my container at equilibrium, and I introduce oxygen. Which of these substances in my original equation will oxygen react with? Well, we already saw earlier that it's not going to react with nitrogen. Those are both already in the air. They don't react with each other. There's no reaction between oxygen and ammonia that happens easily. But we do know that hydrogen and oxygen will react very spectacularly. If you haven't experienced or seen this before, your homework for today is to look for a reaction or a video on the hydrogen balloon. Very exciting. Anyway, so let's pretend that we can do this in a closed container. We introduce some oxygen. That oxygen is going to react with the hydrogen and effectively remove it or decrease the amount of it from our container. Well, since I've removed some of the reactant, the system wants to replace that. And so the system needs to shift back to the direction from where I've removed it. Same idea on the product side. I can't think of anything that would react with ammonia to remove it. Not off the top of my head. Hydroxide. No, that wouldn't do it. I don't know. Anyway, if I could remove ammonia from this container, then the system wants to replace ammonia and shift it to the right. So the nice thing about concentration changes is these are constant. So if you can understand the concept that we're discussing here, there are very rarely exceptions to these. To summarize all of these changes, I have this slide. So again, anytime we add a reactant or remove a product, the system's going to shift right. So that's what's shown here in red. Anytime we remove a reactant or add a product, the system will shift left. And that's what's shown in blue down below. And so that just summarizes what we discussed on the previous screen. In our next video, we'll talk about how temperature changes will shift equilibrium.